Okay, today we are going to be talking about orthogonal functions. These functions are going to be important because are going to be the blocks that we are going to use to construct all Fourier analysis that you know that, well, it is very useful in so many branches of physics. Okay, so we are going to start by the concept of orthogonality in vectors in R3. Okay, we know that there exists something called inner product in vectors. Okay, where the inner product satisfies the next conditions. If we have two vectors u and b in R3, well, we know that the inner product that is represented with this parenthesis between u and b, well, it is going to be the same as the inner product between b and u. This is the first property. The second property is going to be that a scalar, okay, that multiplies u and then we make the inner product with a vector b. This is going to be equal to that scalar times ub, the inner product. Then the third property is going to be that, well, the inner product between u and u is going to be 0 if u is equal to 0, and the inner product of u with u is gonna be greater than 0. And well, in the case of u different from 0, of course. And the fourth property is going to be that u plus b, and I think we need to add another vector here. So the inner product between u plus b and w is going to be equal to the inner product between u and w plus the inner product between b and w, of course. Perfect. So these are the properties that define the inner product. And well, in this case, we are speaking in the context of vectors in R3. But we wonder if we can generalize this concept to other type of mathematical objects. We are going to be interested in the case of scalar functions, okay? Functions that, well, we know very well, functions that have derivatives, that are continuous. Well, we know that we can generalize this if we define the inner product of two scalar functions, for example, f1 and f2. If we calculate the integral from a to b of f1 of x times f2 of x dx, well, we can define this as the inner product between f1 and f2, and you can verify that these properties remain the same if we define the inner product in this way. Okay, and it's also very important that we need to define this inner product on an interval that is, of course, the closed interval a comma b. Okay, so this will be the definition of the inner product. So, what can we say about this? Well, first, we can take motivation from the fact that, well, if the inner product between two vectors is equal to 0, well, we say that these vectors are orthogonal. Okay, so we are going to say that f1 and f2 are orthogonal if, well, the inner product between f1 and f2 is equal to 0. So that means that this integral is equal to 0. Okay, so that is the meaning of orthogonality in scalar functions. And of course, again, this orthogonality is valid only on the interval a comma b. Okay? Perfect. Okay, so a quick example of two functions that are orthogonal. Well, it will be, for example, the functions x squared and x cubed. This is going to be equal to, and in the interval -1 to 1. Okay, well, we are going to take the inner product in this interval, so that is going to be x squared times x cubed dx. And if you make this integral, well, you will see that it is going to be equal to 0. Okay, so that means that these two functions are orthogonal in the interval -1 to 1. Okay, so we can generalize the definition of orthogonality to sets of functions in this case. We can establish that, for example, a set made of functions of one variable like phi0 of x, phi1 of x, phi2 of x, all the way up to, well, infinity. Actually, these sets can be infinite. Okay, we are going to say that this set is orthogonal if, well, we take the inner product if, for example, on the interval a comma b, we take two different functions, for example, phi n of x to generalize, and phi m of x dx is equal to 0. Okay, we say that if we take two different functions from the set and take the inner product of those functions, if we get 0, then this set is going to be orthogonal. Okay, of course, again, in the interval a comma b. Okay, another concept we can talk about is orthonormality. Okay, you know that, well, vector is orthonormal when its size or its magnitude is equal to 1. Okay, so for example, we can have a unit vector u, that is the vector u over its magnitude. Okay, so if we have a set of these vectors that have a magnitude equal to 1, we say that that set is a normal set, or yeah, in the case of the vectors are orthogonal and have size equal to 1, this set is an orthonormal set. Okay, so we are going to generalize that to functions, to scalar functions. So we know that for a vector, the dot product between u and u is equal to the magnitude of u raised to the second power. Okay, so if we see this as the inner product, well, we can say that the magnitude of the vector is equal to the square root of the inner product of this vector with itself. Okay, so in the context of functions, well, we can say that then well, we can calculate the inner product of a function with itself, for example, phi n of x with phi n of x, and this is going to be equal to, well, the integral from a to b of phi n of x squared dx. Okay, and we are going to define this as the magnitude of the function phi n of x. Recall that this is a definition, okay? We cannot say in a rigorous way that this is the magnitude of the function, but we are going to define just to be similar to the definition in the context of vectors in R3. So, and actually this is going to be the magnitude squared of the function, okay? To say that the magnitude of the function, similarly to the vectors, is going to be, well, the square root of the integral from a to b of phi sub n of x squared dx. Okay, so this is going to be like the magnitude of the functions. Okay, so if we have our set of functions phi n of x, okay, if this is an orthogonal set, okay, and for every n from 0 to infinity, we have that the magnitude of phi n of x is equal to 1, then we are going to say that this set is orthonormal, okay? So that means that the magnitude of phi n of x is going to be equal to the integral from a to b and the square root of this. Phi sub n squared of x dx equals to 1. And this is for every n equals to 0, 1, up to infinity. Then we say that the set is orthonormal. Okay, perfect. So we are going to see now an example of a set that is orthogonal. We are going to have that this set is going to be the set of 1 cosine of x, cosine of 2x, and so on and so forth. Well, the general element of this set is going to be cosine of nx. Okay, so to show that this set is orthogonal, well, we need to take two different elements of the set, then calculate the inner product and see that it is equal to 0. Okay, so we are going to begin with the element 1. Okay, we are going to calculate the inner product of 1 with cosine of nx, and we are going to show that this set is orthogonal in the interval minus pi to pi. Okay, so if we calculate the inner product between 1 and cosine of nx, we are going to get that this is the integral from negative pi to pi of 1 times cosine of nx dx. And of course, well, here it's easy to see that this is going to be equal to 0, because when you take the integral of cosine, you are going to get a sine, and this sign will depend on a multiple of x, but x is going to be evaluated on pi and negative pi, but we know that sine of n pi for every n integer is going to be equal to 0. So this integral is 0. Okay, perfect. So we are going to take now two different terms of the set that are, for example, cosine of mx and cosine of nx, and this inner product is going to be the integral from negative pi to pi of cosine of mx cosine of nx dx. Perfect. So if we use a trigonometric identity here, we are going to get that this is equal to 1 over 2 times the integral from negative pi to pi of cosine of m plus n x plus cosine of m minus n x dx. Again, this is a very famous trigonometric identity. And again, if we take the integral of a cosine, we are going to get a sine, and well, a sine of a multiple of x. But again, this x is going to be evaluated in pi and in negative pi, so that that will be a sine of an integer times pi, and that is always equal to 0. So this integral is going to be equal to 0. So we can say that this set over here is orthogonal. Perfect. Okay, but what happens with the normality of the set? Well, for the first term, that is 1, well, we need to calculate the inner product between 1 and 1, and this is going to be equal to the integral from negative pi to pi of 1 times 1 dx. And of course, this is just going to be equal to 2 pi. Okay, but we define this to be the well, the magnitude of the function phi 0 of x squared. Okay, and remember that phi 0 of x is equal to 1. It's just the first element of the set. Okay, so we establish that the magnitude of the phi 0 of x function is going to be equal to the square root of 2 pi. Perfect. So if we remember in the vector context, we would divide the vector by the magnitude of the vector u. But in this case, what we are going to do is to take the function phi 0 of x, which is 1, and divide it by the square root of 2 pi. This in order to create the new orthonormal set. In this case, we see that this set is not orthonormal, okay? It is orthogonal but not orthonormal. But we can construct a new set from this that will be orthonormal. So the first element of that set will be the element 1 over the square root of 2 pi. Perfect. So now we need to take a general element of the set and to take the inner product of that element with itself. So for example, let's take cosine of nx with cosine of nx, okay? This will be the integral from negative pi to pi of cosine squared of nx dx, okay? Well, you know that this is a very famous integral that is solved using the trigonometric identity 1 over 2 times 1 plus cosine of 2nx dx. Okay, and again, if we take the integral of a cosine evaluated at negative pi and pi, we will get 0. And we are just going to get the integral of 1 over 2 dx from negative pi to pi. And it's easy to notice that this integral is just going to be pi. Okay, so to every element of the set, we need to divide it by pi to get then the orthonormal set. Okay, but we know that this inner product is defined as, well, cosine of nx squared, the magnitude, and we see that it is equal to pi. That means that the magnitude of cosine of nx is equal to the square root of pi. And this can be seen as Vn of x. Perfect. So to construct the orthonormal set, well, we just need to divide every term that has a cosine by the square root of pi to get the next set. We will have 1 over the square root of 2 pi, and then cosine of x divided by the square root of pi, cosine of 2x divided by the square root of pi, and so on and so forth to the infinite. Okay, and now this set can be seen as an orthonormal set. Okay, perfect. So here comes the important thing. We know that in Fourier analysis we have functions that are expressed in terms of sines and cosines as linear combinations of these functions. And we have seen that maybe the sine and the cosine turned out to be, well, orthogonal functions. Okay, so we wonder maybe if is it possible to get a linear combination of orthogonal functions that will be equal to a particular function f of x that we are interested in. Okay, so we wonder that, for example, in the interval a comma b, we can define a function f of x that will be equal to, well, a linear combination of orthogonal functions. For example, c0 phi0 of x plus c1 phi1 of x plus c2 phi2 of x, and so on and so forth to the infinite. Okay, so to answer this question, we may need to be able to find these constants c0, c1, c2 to be able to construct the function f. Okay, so it turns out that we will be able to find these constants using the inner product that we have just defined. So what we are going to do first is to multiply all this expression for a particular function or one of the functions that make this set, for example, phi m of x. Okay, so what happens if we do that? Well, we are going to get that f of x phi m of x is equal to c0 phi0 of x phi m of x plus c1 phi1 of x phi m of x plus, and we are going to get all the way up to the term where we have cn phi n of x times phi m of x, and we keep going. Okay, so to be able to use the tool of the inner product, we need to take the integral from a to b, looking that we are working on the interval a comma b. Well, we are going to take that integral on both sides of this equation. So we are going to get that the integral from a to b of f of x phi m of x is equal to, well, the integral from a to b of this quantity times dx plus the integral from a to b of this one over here dx and plus, well, the integral from a to b of this term over here dx, and remember that we keep going. Okay, so looking that these functions are orthogonal, well, we know that if these functions are different, well, the inner product is going to be equal to 0. Okay, so this is 0, this is 0, and actually this is going to be equal to 0. But we are going to have a term on this whole development that corresponds to the term when n is equal to m. Okay, so that means that we are going to have the next result. The integral from a to b of f of x phi n of x is going to be equal to the integral from a to b of cn phi n of x squared dx. Again, the term when m is equal to n is going to survive. So that means that we have two copies of phi n of x, given that this is equal to phi n squared. Okay, perfect. But looking that cn is a constant, well, we can take it out of the integral to get the next relation. Cn is going to be equal to the integral from a to b of f of x phi n of x over the integral from a to b of phi n squared of x dx. And I forgot a dx here and here. Okay, perfect. But remember that at the beginning we defined that f of x was an infinite sum of these orthogonal functions multiplied by some constants. So we can say that f of x can be written as the sum from n equals 0 up to infinity of cn phi n of x. But if cn is this expression that we have here, we can say that f can be written as the sum from n equals 0 to infinity of, well, the integral from a to b of f of x phi n of x dx divided by the integral from a to b of phi n squared of x dx times phi n of x. Okay, perfect. So with this we have answered the question. Well, we can say that it is actually possible to write a function, an arbitrary function f, in terms of a sum of orthogonal functions, or to be explicit, the linear combination of orthogonal functions. And recall that, well, this is just the inner product between f and phi n of x. Okay, so we can rewrite this as the next. F of x is equal to the sum from n equals 0 to infinity of the inner product between f and phi n divided by, well, this integral that we have here. But again, we saw that this integral corresponds to the magnitude of the function phi n of x squared. Okay, we saw that here. It is here. Okay, we saw that the integral of the function squared dx is equal to the magnitude squared. So we can say that this is dividing the magnitude of phi n of x squared. And then this multiplies phi n of x. Perfect. So this will be like the final result of the video, showing that we can express a particular function f in terms of a sum of orthogonal functions, in particular a linear combination of orthogonal functions. Remember that later on this will be very useful to define the basis of the Fourier analysis. So that's why this is very, very important, knowing that, well, a function can be expressed in terms of orthogonal functions. Because, well, if you already know the formula, the famous formula that defines the Fourier series, you know that it says that a function f can be expressed as a linear combination of sines and cosines. Okay, and as you can already suspect, the sine and the cosine are orthogonal functions. Okay, so that would be very related with this formula over here. Okay, so thank you so much for watching the video, and if you have any questions, you can leave it on the comments.